Okay, Assalamualaikum warahmatullah. Bismillahirrahmanirrahim. So today we meet again to continue our online class of Principle of Communication. We are still in chapter 2. So today we will discuss the topic double sideband. We will continue our discussion from previous class, which is about AM amplitude modulation signal. Today's class will discuss about double sideband, uh, DSB, single sideband SSB, and also vestigial sideband VSB. We will discuss also about the process of suppressing the carrier for the AM signal. Okay, so learning outcome for this session is, at the end of this session, the student should be able to describe amplitude modulation signal in terms of SSB single sideband, DSB double sideband, VSB vestigial sideband, and do some calculation on the derived AM. Okay. Second is to compare SSB single sideband transmission to conventional double sideband AM. And lastly, the student should be able to explain some AM application, some amplitude modulation applications. Okay, so before we going further, let's recap about some basic amplitude modulation concept. So in last class, we have discussed about the equation or the formation of AM signal. Okay, so as you know, the modulator is a device that do the modulation process AM. So in AM modulation process, we have two signal. One is the modulating signal. Okay, one is the modulating signal, or also known as information signal. Okay, one. And the second is the carrier signal. Okay, so the modulating signal is the low frequency signal, and the carrier signal is high frequency signal. So these two signal combined together in a process called modulation process. The output is envelope form of AM signal. So the equation for the signal is basically combination of the carrier signal Vc sine to Fct plus Vm sine to pi Fmt sine to pi Fct. So basically the output is the carrier signal plus the product of modulation signal, or the modulating signal, and the carrier signal. So the output is the envelope type AM signal. Okay, so we have discussed this in the last chapter, so we'll go briefly today. Okay, this is the equation for AM signal, where it consists of three parts. Okay, so the signal can be, this signal, when we expand this equation using trigonometry, we get this equation. This is the simplified equation for AM signal, where it has three components. First is the carrier part. The first part is the carrier. The second part is the lower sideband, and the third part is upper sideband. So this signal in time domain can be represented in terms of frequency domain, where the magnitude of the signal and the frequency component of this signal is taken out from the equation and is plotted in frequency domain. So you can see here the carrier with omega c or fc frequency, and ec is the magnitude, and we have here the lower sideband, omega c minus omega m, or fc minus fm, and also the upper sideband, where the magnitude is similar to lower sideband, m ec over 2, and the frequency is fc plus fm, or omega c plus omega m. So this is the AM signal in frequency domain. So we have three components in the frequency domain. One is the first is carrier. Okay, this is the carrier. The second is lower sideband, and the third is upper sideband. Actually, we have another one, the fourth component, which is the information signal here, omega m or fm here, because it is not written in the, it is usually not shown in the graph of frequency domain, because it is considered that fm is far low compared to fc, so you cannot see in the graph. Okay, next. So power relationship. So basically there are three components in the AM signal: carrier, upper sideband, and lower sideband. So basically the total power carried by this signal is combination of those three components, which is carrier, upper sideband, and lower sideband. Okay, so for the transmission efficiency for AM signal, it is represented by this Greek character eta. So this is eta, not zeta. This is eta or eta. The transmission efficiency for AM eta is can be calculated using this equation, where the power of the sideband over total power multiplied by 100%. Okay. So what is the power of sideband? Power of sideband is, because it has two upper and lower sideband, so power of the sideband equal to power of upper sideband plus power of lower sideband. So the power equal to m square over 4 PC plus m square over 4 PC. So we have derived this equation in the previous class. Okay, so m square PC over 4 plus, so it is like 2m square over 4 PC. So it become m square over 2 PC. Okay, so the power, this eta, so this m, this part over the total power multiplied by 100% become m square over 2 plus m square multiplied by 100% is the efficiency, transmission efficiency of AM. Okay, if let's say m equal to 1, where it means that the modulation index is 100% modulation index, 100%. It means that EC equal to EM, or EM equal to EC. So one equal to 100% modulation. The average power PSB equal to 50% of PC, or half of PC. It means that PSB is half of PC. So the transmission efficiency, the eta, will become this equation. Okay, so transmission efficiency eta using this equation, when m equal to 1, so we put 1 into the equation, and it become 33%. Okay, so what does it means? So from this graph, this graph shows the percentage of power, total power, against percentage of modulation. Okay, so the red one is the power in the carrier, and the blue one is the power of the sideband. So basically, you plot this equation, against the modulation. Okay, so from this figure, we can see clearly that when we change the percentage modulation, the power in the carrier and sidebands will change. Okay, will change accordingly. So what we are interested is at percentage modulation m equal to 100%, the power in the sideband is equal to around 33%. So this is 33% here. Okay, the power is around 33% here, and the rest of the power is in the carrier. So imagine that you have a modulation at 100%. When you transmit the signal, all the power 33% or one third, 33.3% is one third. One third of the power is at the sideband, and 2/3 is the carrier, in the carrier. However, our information is transmitted in the sideband. There is no information transmitted in the carrier. So that is quite a problem. Okay. So AM power efficiency problems. There is problem. Information are contained in the sideband only. But the sideband occupy about only 33% of total power, and they are redundant because you have lower and upper sideband bringing the same amount of power, meaning the same amount of information. Most of the power is wasted in the carrier signal. So that is the problem. You send $1, only 30 cents is used. Another 70 cents or 67% is wasted. So we need to solve this problem. Okay. First, how to solve? They propose a suppressed carrier system of AM. Suppress the carrier, remove the carrier. Okay. It is possible to improve the efficiency and reduce the bandwidth of AM signal by removing the carrier. Why? To improve the efficiency. It is possible to improve the efficiency by removing the carrier or one of its sideband. Carrier or one of its sidebands. Okay. Recall from previous section that the carrier has at least 2/3, okay, of the power in the AM signal, but none of the information. So the carrier the carrier has at least two-thirds. The carrier has two-thirds. Okay. The carrier, P carrier, two-thirds. But none of the information. Okay, so we have just now P sideband, one-third, P carrier, two-thirds. So there are various form of AMs. First is double sideband full carrier, contains USB, upper sideband, lower sideband, and carrier. This is the most widely used AM modulation. In fact, all radio channel in the AM bands use this type of modulation. Second is double sideband suppressed carrier. Okay, here comes our discussion. Okay, suppressed carrier contains only upper sideband and lower sideband, no carrier. So this part is gone. A circuit that produces double sideband suppressed carrier is called balance modulator. We will see about this after this. Third is single sideband. So this is also no carrier. In this modulation, only half of the signal of the double sideband suppressed carrier is used. So after suppressing the carrier, then now you remove another sideband. So now you have single sideband. Contains either lower sideband or upper sideband. So this type only have one sideband, either lower part or upper part. This type of AM produce efficient system in terms of power consumption and bandwidth. So in terms of power consumption, this single sideband is considered very efficient because you only send one sideband, one part of the signal which have the information. Okay, no redundancy and no waste. And number 4 is the vestigial. Number 3, even though it has the most efficient system, but it also have disadvantage. Okay, we will discuss later about disadvantage. Number 4, vestigial sideband. This is the modification of the SSB, modification of this single sideband to ease the generation and reception of the signal. To ease the generation and reception. To ease the transmitting and receiving and recovering the original signal. Okay. So this is the frequency domain representation of those signal. So this is the double sideband full carrier. This is the original AM signal. So you have lower sideband, you have upper sideband, and you have the carrier. Lower sideband, upper sideband, and the carrier. So the equation for total power is PC 1 plus m square over 2. This has been shown in previous slide, okay, previous class. Okay, the second one is single sideband. Single sideband with carrier. Okay, single sideband with the carrier or full carrier. So you have either upper sideband or lower sideband, but in this case, you have upper sideband and the carrier. So the total power is P carrier plus this is the m square PC over 4. This is the one of the sideband. Power for one of the sideband. Okay, you have one and one, the carrier and sideband. So the next is SSBSC single sideband single sideband suppress carrier. Okay, now you remove the carrier. So now you don't have the carrier anymore. PC equal to 0, and lower sideband also equal to 0. So now you have only single sideband. Single sideband suppress carrier. So power, total power equal to power of the upper sideband or lower sideband equal to m square PC over 4. This is the total power. So basically, all the power transmitted are the signal having information, the useful signal. Okay, you remove all those not useful part of the signal. Okay, number 4 is the vestigial. So vestigial, what is the difference? Vestigial now has full of upper sideband, okay, full portion of upper sideband, but a little bit, a small portion of lower sideband. So you can see here, the lower sideband is small, small. This is none. Okay, this is small. Maybe after some time, they think that, oh, we might need some of those lower part of the sideband. Okay, and we might also need again the carrier. Okay, so they have the carrier again. For vestigial sideband, um, so here lower sideband is less than upper sideband, the signal. Okay, and they also have the carrier signal again. So the total power is PC plus m square PC over 4. This is the upper sideband plus lower sideband, small one. Okay, small portion of this. Lower is just half of it maybe. Okay, so there is 4 types of AM signal in frequency domain in the power analysis. Okay, so what happened actually? First, suppress carrier AM system. Presence of modulation has no effect on the carrier. Removing the carrier to create double sideband suppressed carrier AM signal should result in a power gain for information carrying, assuming that the power removed from the carrier could be put into the sideband. Note also that the upper and lower sideband are mirror. Okay, upper and lower are mirror image of each other containing exactly the same information. So as we have discussed before, upper and lower sideband is the same equation, same magnitude, same power. So basically it is mirror. It has same information. Okay. So first is double sideband suppress carrier. How we going to remove the carrier? So this is achieved by it can be generated using a circuit called balance modulator. Okay, can be achieved by using a balance modulator circuit where it produces sum and difference. Sum is the plus, sum USB and difference of LSB. Sum and plus, sum is plus, difference is minus frequency, but cancel or balance out the carrier. Cancel or balance out the carrier. So this balance modulator, what it do is it has the sum USB. Sum is the sum means FM plus FC, or FC plus FM. So that is the upper sideband frequency, and difference is different from minus, meaning FC minus FM. or omega C minus omega M. So that is the frequency of low sideband. Okay, but this balanced modulator circuit cancel the carrier. So carrier is gone. The output, the carrier is gone. So now you don't have the carrier. This is called suppressed carrier. So now the frequency domain of the DSBSC is shown here. Okay, so now you have the signal only lower sideband and upper sideband. So now all the power are contained in the sideband. Okay, double sideband suppressed carrier help in reducing power, but bandwidth still the same. Okay, so comparing to full FC, okay, if we compare double sideband suppressed carrier to double sideband full carrier, with or without the carrier, the power is reduced, the transmission power is reduced, meaning that we can save the power where the carrier bring the power. Okay, but the bandwidth is still the same. So bandwidth is still same compared to the full carrier. Okay, double sideband is not widely used because the signal is difficult to demodulate. So this kind of modulation, the disadvantage is it is difficult to demodulate. At the receiver part, the circuit is difficult to process this signal and extract the information. So that is the disadvantage of this kind of double sideband suppressed carrier. So the result is it is not widely used. Okay. Suppressing the carrier. Eliminating the carrier results in a double sideband suppressed carrier shown below. Okay, this is the full carrier signal. This is the suppressed carrier signal in time domain. Okay, time domain. So what happened? So basically this is the normal envelope for AM signal, which is full carrier, double sideband, full carrier. So this is compared to the signal when we suppress or remove the carrier. So here it shows that there is a phase transition. So if we look thoroughly, you can see that the signal has changed here. Here there is no change in terms of the rotation, but here for this signal, some change here, change in phase. Okay, phase transition, some change in phase, where this direction change. Okay, instead of go that way, it go this way. So there is little bit effect on the signal when we remove the carrier. Okay, so let's see. So however, this time domain signal are a little bit just a minor or small change. If you look at glance, then you might not see the difference. Okay, almost the same. Okay, but this part is quite different. This part, okay, compared to this. So this envelope become closer together, come together, no gap. Okay, but in frequency domain, we can see the changes very clearly. Okay, so if we see the signal in frequency domain, okay, the figure here shows the signal, both signal in frequency domain. Okay, so this is the normal normal signal, AM signal, where you have the up lower sideband, you have the carrier, and you have the upper sideband. Three component of the AM signal. So now this signal, the example is the carrier is around 5 kilohertz. Okay, the frequency is around 5 kilohertz. But this signal, suppressed signal, so now you see that there is no carrier. Carrier is not exist anymore. Okay, only the sideband is exists in this frequency domain signal for suppressed carrier AM signal. As the name shows, suppressed carrier, so the carrier is gone. It's removed from this signal. Okay, so basically you cannot derive straight away from this signal to this signal. What you do is you connect the signal to the spectrum analyzer in order to get this kind of signal in frequency domain. You use spectrum analyzer, so it gives you the signal in frequency domain. Okay, let's see the equation. So AM double sideband suppressed carrier equation. So this is the full AM equation, the normal AM equation. So you have here is carrier part. Sorry, yeah. So you have here the carrier. Okay, and this is the lower sideband, and this is the upper sideband. Upper, it has plus sign, and lower it has minus signs. Okay, so removing the carrier signal, the equation becomes like this. So you remove this one, remove this carrier signal. So the double sideband suppressed carrier become this equation. Okay, so V double sideband suppressed carrier equal to MEC over 2 cos omega C minus omega M T plus omega MEC2 over 2 cos omega C plus omega M, this part only. Okay, now you got the equation for double sideband suppressed carrier. So let's see the power distribution. Okay, so P total equal to P lower sideband plus P upper sideband. So there is no carrier. Carrier is already removed. So solving this equation, so we have seen this equation. What is this? So basically this is the RMS value. EM over 2 is this part. EM over 2 over cert 2 is the RMS value. So square, RMS square over R. So this is this part is for LSB and this part is for USB. So solving this equation, we get E square M over 4R. Okay. In double sideband suppressed carrier, all the power transmitted is sideband's power. If R equal to 1 ohm, so solving this equation become, if this 4 is this R equal to 1, then solving this equation, PT equal to E square over 4 equal to PSP. You still remember this number? You can see from previous equation that this is the sideband power. Okay, therefore the efficiency eta, the transmission efficiency eta for this single sideband double sideband suppressed carrier is 100%. So it is very efficient. Efficiency 100% is very efficient. Okay, but you still have the problem. You don't want to send two signal or two signal bring the same information. You just need one, okay? So then it comes a single sideband. Okay, single sideband modulation. One sideband is all that necessary to convey information in a signal. See, one sideband only enough. One sideband is enough. All it needs to convey information. So a single sideband suppressed carrier. So now we don't have that. We don't want double. We want only single. Single sideband suppressed carrier. Signal is generated by suppressing the carrier and the sideband. So now you don't want that double sideband. You need only one sideband. So after removing the carrier, you need to remove another sideband. Okay. So single sideband modulation benefits spectrum space is conserved and allows more signal to be transmitted in the same frequency range. Now, spectrum space, the frequency is conserved, dapat dijimatkan, is used little used. Spectrum space is saved and allow more signal to be transmitted within the same frequency range. Okay, if you have, for example, 1 kilohertz previous double sideband, you can send a double sideband in, if 1 kilohertz FM, so bandwidth is 2 FM, right? 2 kilohertz. So mean that you need 2 kilohertz to send the signal. But if you send 1, you can save half of the frequency range. So you just need 1 kilohertz. Okay. All power is channeled into the single sideband. So you just need, what you send is just that sideband. So all the power you send is just for that single sideband. This produces a stronger signal that will carry further and will be more reliable. So it will produce stronger signal and it will go further. You can send longer distance and it will be more reliable receive at greater distance. So you can send the signal to greater or to longer distance and it will be strong. So even the location is longer, is further, but the signal will still strong. Okay, compared to double sideband, if you're using the same amount of power. Okay, occupied bandwidth space is narrower. Okay, the bandwidth used is narrower and noise in the signal is reduced. Okay, so basically you can reduce the noise if you use this single sideband modulation. Number 4 is there is less selective fading over long distance. So over long distance there is less fading. Fading is kind of distortion or loss lah, basically kind of loss. So over long distance the loss is less, is minimized. Okay, there is the benefits or advantages of single sideband compared to double sideband. However, it also have disadvantage. The disadvantage, the first is single and double sideband are not widely used because the signal are difficult to recover. So the signals are difficult to recover or to demodulate. The demodulation part is complex, is difficult. The second one is at low power, pilot carrier is sometimes transmitted along with sideband in order to more easily recover the signal at the receiver. So basically, you still need the carrier in order to easily recover the signal, demodulate. Okay, the issue is in terms of demodulation, where the receiving part, it is difficult to demodulate for this single sideband and also double sideband without the carrier. So you still need the carrier. Okay. So let's see the equation of single sideband surplus carrier. From full AM equation, okay, the equation derivation always start from the conventional AM equation. Okay, you still remember where it has three components. First is the carrier, second is the sideband. This is the with minus sign. This is the lower sideband, and this is the upper sideband where it has the plus sign. So remove the carrier signal and one of the sideband of the equation becomes, so you remove this part and you remove this part. Okay, oh sorry, so you can either you remove in this case they remove the upper part. Okay, let's say, okay, so you remove this part. So now you have this lower sideband only. Remove the carrier signal and one of the sideband, the upper sideband. The equation become lower sideband MEC, this one, cos over 2 cos omega C minus omega M. So this is the lower sideband. Or you can remove the lower sideband and you have upper sideband. So upper sideband MEC over 2 cos omega C plus. This is this part. You remove this part and you get the upper sideband. Okay. Let's see the signal in time domain. So if you see in time domain, the signal is almost the same, but this is the lower sideband and this is the upper sideband. Okay, of course, the lower sideband is slightly less frequency compared to upper sideband. So you can see from this figure that the upper sideband frequency is slightly higher compared to lower sideband. Of course lah, because this frequency range, this is minus, this is plus. So the carrier frequency plus information or the modulating frequency, so it is higher compared to the carrier frequency minus modulating frequency. Okay, so in frequency domain, this is what. So this is in frequency domain. Now this frequency signal show the modulating signal frequency here, omega M or FM. So this is the modulating signal at omega M, and this is the lower sideband signal at omega C minus omega M. So now you have, if single sideband signal, you only have this part lah. This part. Without this, there is no, you don't send this signal. So we are discussing about this. So, but in another one is if you have the upper sideband, you have slightly higher frequency compared to lower sideband. The upper sideband is slightly higher frequency. It is the same. Okay. So comparison. If we compare the signal, four signal. So what we have here, the carrier, audio, AM, and single sideband. So of course, you know the carrier. So this spectrum, FC, carrier is FC. So then you have the modulating signal or audio signal, very low signal. So there is no, it is not shown in the spectrum. Actually, it is here, down here compared to FC. Okay, so AM, conventional AM signal, you have three component of FC, lower sideband, and also upper sideband. Lower, FC, and upper sideband. Okay, but for SSB or single sideband suppressed carrier, the signal is almost similar to carrier signal. Okay, the frequency is almost similar to carrier, but it is slightly higher, right? This is the carrier, this is only one sideband, slightly higher. Or you might have another one here. If you have single sideband, which is lower sideband, you have the spectrum here at this part, but only one, only one. So that is the comparison between carrier, audio, AM, and single sideband in terms of frequency domain and time domain. Okay, this is the calculation for signal power consideration, single sideband. PT equal to PT means the total power transmitted equal to power at lower sideband only. Okay, or total power transmitted equal to the power at upper sideband only. So this is the equation, EM over 2 Z2 square. So this is what? This is the VRMS square over R. So becomes this equation. So same. Therefore, the power transmitted is equal to the power at USB only. So now we can say, we can prove that the efficiency, because of the transmission not included the carrier, the eta, the efficiency is 100%. Okay, signal power consideration. In SSB, single sideband, the transmitter output is expressed in terms of peak envelope power. Peak envelope power, what is that? PEP, the maximum power produced on voice amplitude peaks. The power on the amplitude peaks. Okay. Envelope. Carrier power is useless. Carrier power is useless as a measure of the power in double sideband suppressed carrier or single sideband suppressed carrier, because there is no carrier. Okay, you remove the carrier, so you cannot rely on carrier power anymore. Okay, why? Because the carrier is not existed. It's not existing anymore. So the carrier power is theoretically 0. Instead, the peak envelope power is used. So for the signal without the carrier, they measure the power in terms of peak envelope power. Okay, what is that? Peak envelope power. Okay, why use PEP in suppressed carrier and in single sideband suppressed carrier and double sideband suppressed carrier? When the power for double sideband full carrier is measured, the steady measurement is obtained regardless of the modulation. Okay, So normally in full carrier double sideband, they measure the power, the carrier power. When the power for double sideband is measured, steady measurement is obtained regardless of the modulation. The power average over a second or less is constant. This is not the case for single sideband suppressed carrier, as no carrier present, sideband only appear when modulation is present. So when there is modulation is present, there is power. Okay, and power is proportional to the modulating signal, the audio at that instant. As a result, the power of the transmission is limited by peak handling capability of the transmitter. Accordingly, a measurement known as the peak envelope power is used. The peak envelope power needs to be measured by power meter with a short time constant. Okay lah. So of course lah, power measurement is using power meter. Okay, types of power measurement. Okay, there are 3 types of power measurement. First is average power, normal. So this is continuous wave radio frequency signal, high frequency signal, average power. This is what we have calculated just now. VRMS square, right? Okay, the second one is pulse power. So this kind of signal is measured from pulse RF signal. Okay, pulse RF signal, you measure pulse RF, pulse power. The third one is peak envelope power. So peak envelope power is measured using Gaussian pulse signal. So this is the technique to measure power for double sideband suppressed carrier and single sideband suppressed carrier. They are using this peak envelope power. So peak envelope power, if you have this signal, this is the envelope. So now you can see that this is the power plot against time. Okay, so there are a few terms. First is PET, is the envelope power. So this is the envelope power. This is PET. This is PEP is the peak envelope power. Here, PEP. So this is the envelope. So this is the envelope. PEP is the peak envelope power. PT is the instantaneous power. PT, this was the PT. And P average is the average power. P average. This one. Okay, PP is defined as the average power in the transmission line over the 1 RF cycle. Limited by modulation envelope, peak instantaneous power represents the excursion of RF waveform beyond modulation envelope. So there are various or some few kinds of power which is related to peak envelope power, PEP. Peak envelope power, it is simply the power at modulation peaks calculated using RMS formula. So when you measure power, you always use RMS. So V peak over square over root 2 square over RL. Okay, so this is the equation for peak envelope power. So VRMS square over RL. Okay, peak envelope power in watt, V peak voltage in volts, RL is load resistance in ohm. Okay, example, you can try this example. An SSB single sideband transmitter produces a peak-to-peak voltage. Okay, now you have V peak-to-peak cross 75 ohm antenna. What is PEP? So now you have this V peak to peak, you need the equation is in V peak. So you need to divide this to 2. Okay, divide into 2, you get the V peak. So from V peak you get the VRMS. Okay, divide by Z2. VRMS is V peak over Z2. Okay, this put into the equation. This is VRMS square over R. Load resistance 75 ohm. So you get the equation. Now you get the answer. Okay. Next is, okay, you can do this on your own. You have the RL and V peak. Okay, you can calculate yourself. Okay, the last one is the vestigial sideband VSB transmission. Vestigial sideband VSB transmission is the modified AM transmission in which one sideband, the carrier, and only a portion of the other sideband are transmitted. So for vestigial sideband, you have 3 components again. Okay, you have sideband, one sideband, carrier, and portion or part of the other sideband. So you still need the carrier and half of that, or a part of that sideband, another sideband. Okay, this kind of signal is widely used in TV transmission. So if you see the TV, so basically this TV is using AM frequency and it use vestigial sideband transmission. Okay, so this is the frequency domain of the vestigial sideband. So you have, this is the modulating signal, the information. Okay, you should put like this lah. Okay, not connected, not straight. So this is the upper sideband. This is upper part of the sideband, and this is the portion of sideband, and this is the carrier. So vestigial sideband consists of carrier, upper sideband, and part of a lower sideband, and the equation becomes like this. Okay, so you can that's all for today. Okay, we will continue on another part with another topic. Okay, hope you understand, hope you enjoy this class. If you have any question, you can always ask me in YouTube or in Kalam or through WhatsApp. Okay. Thank you very much for your attention. That's all. Assalamualaikum warahmatullahi.